right, so we're going to look at a phenomenon known as total internal reflection. We have learned about refraction. We have learned about reflection. If you haven't, go back and check out those mini lectures and example problems and all of that. We're going to put both of these ideas together, actually, for a phenomenon that's really cool and really impactful and is really important for our technology and our communication today. Okay, so we're going to do a little quick reminder of the idea of refraction and what happens as rays of light go from one medium to another. So here I have a boundary, and on this side of the boundary, I have an index of refraction. We're going to call that NA. And this side of the boundary, we're going to call NB. And in this case, NA is greater than NB. NA is greater than NB. All right? So we know, because the index of refraction of A is greater than the index of refraction of B, that the light that goes from A to B is going to refract in a certain way. So let's look at how it would refract. If I had a ray of light incident on this surface coming from A going to B, I would of course draw my normal. And because A is greater than B, the angle of refraction is greater than the angle of incidence. This is my angle of incidence. My angle of refraction is going to be greater than the angle of incidence. The light bends away from the normal when we go from an area of high index of refraction to an area of low index of refraction. Based on Snell's law, the ratio of the angle of incidence to the angle of refraction, the sine of the ratio of the sine of those angles relative to the ratio of the indices themselves, we know that as I continue to increase my angle of incidence, my angle of refraction is going to continue to increase. So if I make my angle of refraction, or excuse me, of incidence larger, then I get an angle of refraction that is larger. So I start out with a steep angle and I get a pretty shallow angle of refraction. Then I make this a little bit more shallow and I get an even bigger angle of refraction. And if I keep doing this all along the line, so now I'm going to make an even bigger angle of incidence. There's going to come a point where my angle of refraction is really, really, really close to the surface. And if I go just a hair more, my angle of refraction is going to hit 90 degrees. It's going to be at the surface. And what if I go just a little bit further? What if my angle of incidence would make it even more? Well, I end up with a reflection. So now that R represents reflection, I end up with the light ray being reflected rather than refracted. My refraction angle has hit 90 degrees, and if I go one smidge more, now it becomes reflection. So this angle is called the critical angle. This is the angle of incidence where the light goes from refracted to reflected. And it's that boundary that we care about. Well, if that were the case, if I put another tube here, another boundary there, so I made a wire, well, this is just going to pass this straight line, and now this angle and this angle and this angle are the same. I'm at the critical angle, and I don't refract, but I reflect again. And this bouncing reflection is what we call total internal reflection. It happens at that critical angle for a given substance boundary difference. Remember, it's the difference in those mediums that's going to play a role. And what is this used for? To Well, this is fiber optic cables, right? This is sending information via light really, really efficiently and really fast, all through internal reflection. And once this boundary is open, we see that light. You also see those in those fun night toys that you can get at the county fair or the carnival. So check out the little mini lecture video of the light demonstrations, both of hitting total internal reflection with our razor lay box in that demonstration, as well as the sort of fun toys you can get at the carnival. So understanding refraction, what happens as I go from high to low and I get more shallower and shallower, a larger and larger incident angle, I end up at that critical angle, which is then reflected at that same angle, and my light continues to bounce unrefracted, fully reflected throughout the cable. All right, good job.